I'll be quiet and let you take it away. Thanks.
Thank you. So I guess it's written there. I'm going to talk about filtered instanton Floer homology and the how to use this to get at cosmetic surgery problems, or more generally, how to try and show that two things are not diffeomorphic using instanton Floer homology in a realm where you can rarely ever compute these things. I think some people might have heard some of this before, so sorry for boring you, if so, but hopefully there's something new for everybody. Um, so I've got this in three parts here, and it's fortunately built into the name itself. I'm going to start by talking about what I mean by filtered Morse theory, then give a quick reminder, though I don't know how much we need it here, about instanton Floer homology, and then finally get into how I can use this to say something about non-diffeomorphic manifolds. So the starting point is this old observation, which is that if I start with a Morse function on some smooth closed manifold X, then I mean we I think all know that we can go from here to a Morse homology which computes the singular homology of X using critical points and flow lines. But in the case that we're interested in today, we don't just have, it's not just the smooth manifold that we care about. Instead of just picking a smooth function and using that in an auxiliary way to construct a complex and compute homology, in the situation we're going to look at, we have a space with a canonical function on it. We're given the Morse function. It's part of our data. And in that case, there's a natural way to filter the homology of this thing. If you want to cut off your complex at level R, just throw out all the critical points whose value is less than or is larger than R. In practice, if I'm drawing a picture of this, I take, say, the two sphere, where F is the standard height function. Then we're looking at the homology of the empty set for R less than 0, the homology of a disk for R between 0 and 1, and the homology of S2 when I finally get up to that. No, that's not how height on the sphere works. Great. Fixing that, what we see is we see these homology classes popping into, and in other cases, disappearing out of existence as we change R. And we might be interested in, well, when is the first time I see the second homology class? The only time I'll see that is when R is at least 1. So I can get some numerical information out of this. The first time that second homology class exists is at level 1. 1 is an important number for this Morse function. That's my filtered bit. That's filtered Morse theory. The relevance to us is if I take a closed oriented three manifold Y, then we get a canonical smooth manifold. The infinite dimensional space of irreducible SU2 connections on Y up to gauge transformations. And this comes with a canonical, well-defined function, the Chern-Simons functional. This is kind of crazy compared to what we see in every other Floer theoretic gadget we work with. The function itself, not the set of flow lines, but the function itself is purely topological. By contrast, the Chern-Simons-Dirac functional is defined with respect to a metric. By contrast, the J holomorphic curve equation needs us to pick an almost complex structure. Talking about Rabe orbits means we need to choose a contact form instead of a contact structure. Most of these Morse homologies we work with are depending on some auxiliary geometric structure, which we then show it doesn't depend on. There's some of that here. This is not usually a Morse function. On the other hand, we can look at, well, let's take that perturbation down to zero. We can always find an appropriate Morse perturbation. I'm going to kind of sweep that issue under the rug and pretend Chern-Simons is always non-degenerate. I can always talk about its Morse homology. Here, the perturbations play a different role than extra geometric structures do. When you're picking a metric, there's not a zero metric to reduce yourself back down to. Here, there's a zero perturbation you can limit to. So I'm just going to pretend this is always a Morse function. If you work with integer homology spheres, there actually is a well-defined Morse homology. Which is well-defined, independent of perturbations and whatnot. And I don't know, that launched the field of instanton gauge theory for the past 35 years. I spent all this time talking about filtered Morse homology, where you have a function to R. And where is it? Here I've got a function to R mod Z, which is not R. I cannot take the set of angles less than pi or anything like that. I'm just going to wrap back around. To make sense of this use of filtered Morse homology, you need to unwrap this. The fundamental group of this space of irreducible flat connections on Y is the integers. The map from this group to the fundamental group of the circle under Chern-Simons is an isomorphism. If we pass to the universal cover, we do have a well-defined functional. a well-defined R-valued functional, where here I'm using the tilde to indicate universal cover, as opposed to equivariant in some sense. Now there's a Z action on that universal cover. And this Chern-Simons function is appropriately periodic. If I write X for a generator of that fundamental group Z, then Chern-Simons, the lifted Chern-Simons moves up by 1 as I translate in the universal cover. Now, we can actually try and run this filtered Morse homology strategy to this thing. We get groups arising as the filtered Morse homology of this universal cover with respect to the lifted Chern-Simons functional. And skipping some technical detail about Chern-Simons values, this gives well-defined groups for every value R from R to infinity. When Y is an integer homology sphere. These fit together in a compatible way. If you take a larger cutoff value, possibly infinity, so that we're just taking the instanton homology itself, there's a natural map from the R cutoff instanton homology to the S cutoff instanton homology, and these are compatible in the obvious sense. Finally, we have a certain periodicity property. Instanton homology is usually only Z graded. When you move up to the universal cover, you get rid of the spectral flow. Instanton homology is usually only Z mod 8 graded. When you pass to the universal cover, you get rid of the spectral flow issues that cause that. So you get a Z graded group. However, the filtration and the grading are kind of affinely related. If I increase the grading by 8, my filtration goes up by 1. In other words, the R plus 1 filtered part of the degree D plus 8 homology is the R filtered part of the degree D homology. And that's compatible with all this other structure. Phrased like this, this first appears in the literature in work of Nozaki, Sato, and Taniguchi. Where they don't just prove that you get some well-defined groups. If we just got groups, we wouldn't be that excited by instanton homology. You also get a sort of functoriality. First, this is an oriented diffeomorphism invariant. Which follows from second, if I hand you a cobordism from Y to Y prime, which is homologically simple, B1 equals B plus equals 0. We have a natural induced map compatible with all those inclusion maps above, from the R-filtered instanton homology of Y to the R-filtered instanton homology of Y prime. This plus some functoriality for composites of these is what gives you that diffeomorphism invariance, independence of perturbation to begin with. They use this for the purpose of homology cobordism invariance. They have this lovely theorem that there's a whole host of manifolds that can't bound any definite four manifold of either sign. In particular, they do this by introducing a numerical homology cobordism invariant. Roughly, what's the first R for which some special class in this group becomes non-zero? And that special class relates to the equivariant structure on instanton Floer homology, which I'm totally avoiding talking about today. It's not going to be relevant for me. But their upshot is that if I take, for instance, 2 copies of the Poincare sphere together with 1 copy of minus sigma 2, 3, 11, this bounds no definite four manifold. And really, I'm just mentioning one in a long history of great results about homology cobordism proved using the Chern-Simons filtration. The first one that comes to mind immediately being Furuda's work showing the homology cobordism group is infinitely generated. But a lot of this links directly back to homology cobordism, somehow having to do with the trivial connection, which I'm ignoring in this instanton homology. And most of these other invariants pay attention to relationships with that trivial connection in some way. Instead of homology cobordism invariants, let's do something extremely naive and write down a numerical diffeomorphism invariant I can get from this. When I was on this picture over here, I asked something along the lines of, well, what's the first time I see that second homology class? The first time I see it is at R equals 1. What's the first time I see that 0th homology class? The first time is at -1. So I record that information, -1 and 1. These are the first times some homology classes appeared. We're going to do the same thing here. Going to define a function which takes integers as input and as output produces a real number or possibly infinity. And define this by exactly that procedure I suggested. Take the least, maybe I should write the infimum here. Oh, I don't know what I did. Okay, great. Over all R, such that the map from F sub R, instanton homology, to instanton homology itself we take the smallest R so that this map is non-zero. For R going off to minus infinity, this group is eventually 0 in a fixed degree. I'm sorry, this is not clearly phrased. I mean to say, where did D come into this? I'm specifically looking at the homology classes in degree D. In a fixed degree, as R goes to minus infinity, this is just 0. So this infimum can't be minus infinity. On the other hand, as R goes to plus infinity, eventually I have all the flat connections in that homology class. So eventually, for large enough R, this just coincides with ID. So in particular, this invariant is non-trivial, less than infinity, if and only if Floer's instanton homology in degree D is non-zero. So this invariant is non-tautological, not just always infinity, so long as instanton Floer homology isn't just zero. I would love to know that that's always true for integer homology spheres other than the three sphere. It's not currently known, but you should imagine that as being not really a big restriction. It's very plausible that every integer homology sphere other than the three sphere has non-trivial instanton Floer homology. And in that case, that would mean for every homology sphere other than the blah, 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 other than the three sphere, this kappa y has something to say. It has some non-trivial information in it. The second basic property of this invariant relates back to this periodicity I mentioned earlier. If you just run with the definition for a bit, you find that what that periodicity gives you is that kappa y is, in a sense, periodic. If you shift its input, the output shifts predictably. Kappa y of d plus 8 is kappa y of d plus 1. And finally, this is a diffeomorphism invariant. So if I'm going to try and use this to distinguish 2-3 manifolds, I need a way of distinguishing these functions. And the answer had better not be compute them, because I can count on one hand the number of integer homology spheres I can compute this for explicitly. Maybe two. I guess it depends on how much work I'm willing to put into going through Fintuschel-Stern's instanton homology paper. But it's tough to compute this, and trying to compute this is not a good way to use this tool. We instead want some general theorems which help us understand when two things will have these invariants be distinct. I'm sorry, I just realized I forgot to mention a very important part of the Nosato work earlier. See if I can make some space for it here. Yeah. Okay, I think maybe I will fix this a little later and just try and make the point I wanted to make right now, which is that they have one stronger fact about this functoriality. Roughly, the difference between an input and an output of this map in terms of their Chern-Simons filtration is the energy of an instanton connecting them. That energy is positive unless it's a flat connection, which can only happen if the fundamental group of W is non-trivial. Which means that necessarily instantons going from flat connections moving from the left side to the right side have to decrease energy. So when the fundamental group of W is trivial, this map factors through a lower filtration. And that constant eta is not dependent on R. It filters through a consistently lower filtration for all R. Sorry for not mentioning that. That's an important part of their work. That's part of how, I don't know, that's an important part of why these invariants are powerful, and it's about to be what I'm referring to, about to be what I use. The way of distinguishing these that I have in mind, and another thing I think I forgot to mention earlier, is that this is all joint work with Ty Lidman, is using the functoriality of Nozaki Sato and Taniguchi. We prove the following theorem, allowing us to distinguish these manifolds. Suppose you have the following type of cobordism, which is going to be an extremely restrictive class. First off, it should be simply connected and negative definite. Second off, so that these kappa invariants are not trivial, we should demand that the instanton homology of Y is non-zero. And third off, this is the hardest thing to satisfy by a long shot. This cobordism map should induce an isomorphism on I star. Then in this case, we actually can distinguish the invariants kappa y and kappa y prime. Y is not oriented diffeomorphic to y prime. Just to discuss the proof very quickly, because it's straightforward from the definitions and from the work of Nozaki, Sato, and Taniguchi. First off, because instanton homology in degree D is non-zero, kappa y of D is finite. Second off, if the value is R, then we have a compatible diagram. Well, I have this map from FRID over to ID, which I know is non-zero because kappa y of D is R. I also have a compatible map to FR minus eta of Y prime because the cobordism is simply connected. Energy must be positive. Filtration must decrease as I move from one side to the other. By assumption, this right map is non-zero. Sorry, by this assumption, this right map is an isomorphism. So the composite is non-zero. So the bottom left composite is non-zero. So this map is non-zero. And therefore, whatever kappa y prime of D is, it's strictly less than kappa y of D. They're different manifolds. This isn't the main thing I want to use today. These aren't the kinds of cobordisms that will help us with cosmetic surgery, but it's a bit of a warm-up. In particular, we do get some applications straight out of this. If I have a knot in S1 cross S2, with the same homology class as S1 cross point, which is non-trivial. It's not isotopic to S1 cross point. Then all the integer homology spheres I can get by surgery on this knot, the integer surgeries on this, are distinct. In other words, all the Maser manifolds with two handle attached with the same along the same knot, but with distinct framings are necessarily distinct. You can upgrade this to not even ribbon homology coordinate if you want, but that's maybe not too surprising once you know they're not diffeomorphic. And to see this, I'll give away the second key tool in trying to use this result. The hard part is finding a map which induces an isomorphism on I star. If that's going to happen, you should have a good reason to know that that's true. It's probably not going to happen by pure luck. Well, where do I see things which constrain the behavior of a map? From exact triangles. Each of these sits into a surgery triad with the next. Where the third manifold is S1 cross S2, equipped with a non-trivial admissible bundle. I have to say something like that to make sure this is even a meaningful description down here. I don't know what instanton homology of a manifold with B1 positive should mean. But if I equip it with some suitably non-trivial SO3 bundle, there's a well-defined homology group. And for S1 cross S2, because it has no non-abelian representations of its fundamental group, that homology group is just 0. This map up top is defined by a cobordism, a two-handle cobordism, and it's an isomorphism. The cobordism has all the desired properties. It induces an isomorphism on instanton homology. Pi1 is trivial. B plus is 0. And finally, some work of Lidman, Pinzon-Caicedo, and Zentner implies that the instanton homology of these Maser manifolds is necessarily non-zero. So we have the strict inequality. N surgery and N+1 surgery are not diffeomorphic because instanton homology gives an isomorphism from each to the next, because this cobordism gives an isomorphism from each to the next. As a result, all of these have non-trivial homology in degree D. So I get a sequence of such inequalities. And so N surgery and M surgery for M larger than N has a smaller kappa invariant.
Hey, Mike.
Yeah.
Just to show that someone's listening, everywhere you've written S3, you mean S1 times S2.
Yes.
So just you can fix that for the notes.
Yes, thank you. I'm actually just going to write S because all I meant was surgery. I know I should have fixed that later, but it was going to bug me if I didn't. Thank you very much for pointing that out. Okay, so we've proved this corollary. We've proved that these manifolds are distinct for N other than M. I have a little more time than I thought I did so far. If there's any questions, I'd be glad to take those before moving on to the last bit.
So just to, maybe you're about to talk about cosmetic surgery problems, because this is sort of a cosmetic surgery problem for S1 cross S2, but so you're going to tell us now about
S3 itself.
S3.
Yeah.
Okay, all right.
Yeah,
So
exactly.
then I won't ask any more.
Okay. In that case, maybe I should move on and use the extra time to either go into some more details or take more questions at the end. But yeah, you're exactly right. The reason this worked is because Floer's exact triangle, as he wrote it, needs you to have an admissible bundle as one of the terms. Also, an admissible bundle, an easy admissible bundle that I know has zero instanton homology is the non-trivial bundle over S1 cross S2. So if I'm looking for places where I can use Floer's triangle to prove that that map is an isomorphism, that's about it. We'll need a variation on this result, which I'll talk a little bit about, which handles the case of the bundle having the cobordism having some non-trivial bundle on it, or possibly B plus is positive, or possibly there's a sort of family of metrics on this. I guess let me talk about that a little bit later. Anyway, these conditions on W can be much relaxed so that we could maybe say something about surgeries in S3 and not just surgeries on knots in S1 cross S2. And as Danny said, our goal here is really the cosmetic surgery conjecture in S3. If K is a knot in S3 other than the unknot, then surgery with, if two surgeries with different parameters are oriented diffeomorphic, in fact, they were the same parameter all along. There's plenty of good great partial progress on this. I don't want to understate how excellent these results are and the tools used to get them. Two in particular are Ni Wu's result that in the situation of the cosmetic surgery theorem, if I have two slopes that give me the same manifold, in fact, the slopes must be opposite to each other. Either they're the same slope or one is negative of the other. And strengthening this, Hanselman proves that in that situation, you can actually constrain the values of T quite a lot. The positive term could be 2, could be 1, could be 1/2, 1/3, 1 over n for general n, but that's it. So in principle, the cosmetic surgery conjecture in S3 is now a countably infinite sequence of individual problems. And our contribution here is to make that from a countably infinite list of problems to countably infinite minus 2. We can rule out 2 of these cases. And as far as I can tell, without some serious modifications, this argument is not going to cut it to get to any of these other cases. I would love it if someone had any idea for extending this. As for 1/4, you get there from a cabling trick using 1/2 surgery on the 2-1 cable of a knot. The main real argument, the main place something really happens here is the case of 1/2 surgery. So let me argue about what's going on there. There's two ideas, maybe, I don't want to count them. There's a small number of ideas circling around here. The first is that I can fit 1/2 surgery and -1/2 surgery into a surgery triad. That's special to this case. I don't know how to, I mean, I think this is not true otherwise. And certainly this description does not work. If I add a 2-framed meridian around K, then 0 and 1 surgery on K and then 2 surgery on that meridian gives me -1/2 and 1/2 surgeries on K. If I took infinity surgery on K on the left, I'm left with just 2 surgery on that unknot. In other words, I'm just left with RP3. So what I have is a surgery triad, and our first job is to show that there's still a notion of instanton Floer homology exact triangle in this setup. This is mainly following through the usual argument of the exact triangle, being a bit more careful of some reducible solutions that might appear that you have to rule out in some way. But what Floer's exact triangle would give you, if you believe it can be extended naively, which I promise it can.
Mike, when you say the usual, do you mean the sort of floors changing the perturbation to get a triangle?
Oh yeah, I should. That's fair. I'm referring to Floer's exact triangle, and that's not how he proved it. I mean the modern versions of this proof, like the one in lens space surgeries, KMOS, the families of perturbations. Is that what you were looking for, Dave, or should I clarify?
Yes. Yeah, exactly. I know several proofs.
Yeah. It's that one specifically that's going to be helpful for me here. And actually, it's going to be helpful for a very specific reason. What you end up with is an exact triangle relating these two groups and a sort of twisted homology of RP3. RP3 equipped with a certain non-trivial but not admissible bundle. So this bottom group, however it's defined, it's not usually defined in the literature, is 0. So this induced map up at the top, W star, gives an isomorphism. But I have bad news. And I'll call this maybe W naught. It's simply connected. I star of W naught is an isomorphism. But B plus of W is equal to 1. you still get a sort of inequality, just like we did back here for these kappa invariants, but the inequality doesn't end up giving you any sort of information. You get an inequality that is not interesting. You could easily believe that that inequality is compatible with the cosmetic surgery conjecture. However, you can spell out in a bit more detail how the exact triangle actually gets proved. There's not just one cobordism W naught involved. Whoops. There's also a cobordism W1 from half surgery to RP3, and a cobordism W2 from RP3 over to minus 1/2 surgery of K. And what we'll end up using here is that it's not just that the instanton homology of RP3 is 0. The instanton chain complex of RP3 is 0. Normally, what the proof of the surgery triangle does is it shows that this composite is null homotopic. It gives a chain null homotopy of that composite. I'm going to write W12 for that composite and I for a certain family of metrics on that composite, interpolating between lengthening the neck where the RP3 is and alternatively splitting off a copy of CP2 bar. This gives a map from the 1/2 surgery complex to the minus 1/2 surgery complex, which gives a null homotopy of the induced map. Apply the W1 chain map, apply the W2 chain map. But this is where the magic happens. That induced map is 0. It factors through the 0 chain complex. This map is not a null homotopy anymore. It's actually a chain map of degree, I don't know, like +3 or something like that, from 1/2 surgery to minus 1/2 surgery. Further, if you look into the relations on the exact triangle, when one of the complexes is just 0, you'll see that the relations you're actually showing are that, whoops. You dig into the details, you'll see that what you're really doing is showing that W naught is an isomorphism by constructing a chain homotopy inverse to it, given by this cobordism with that family of metrics. So this chain map induces an isomorphism on instanton homology. It's simply connected, and it's negative definite. There's some subtleties here. Well, there's this family of metrics, and there's this there's this family of metrics, there's this non-trivial bundle you have to pay attention to. But after some fiddling, an argument much like the one before implies that 1/2 surgery can never be diffeomorphic to -1/2 surgery. We show that the kappa invariants are necessarily distinct from one another. I could talk a little bit more about how that goes exactly, but frankly, it's really just the same idea as this argument back here. I have this isomorphism. I get an inequality on the kappa invariance. It's not quite as simple of an inequality as this one was, but it's enough to prove the desired result when you add in periodicity of these kappa invariants. So maybe I'll stop there and say that, I don't know, Chern-Simons implies cosmetic surgery for 1/2 and 1/4 slopes. And if someone can find a better family of metrics that'll help us tackle 1 surgery or a 1/3 surgery, I would be very happy to hear that.
Are there further questions or questions now that we've won?
Well, I think we're all winners here, so thank you. So is what you were saying, just before you said we win, is that this like the other maps, more or less by construction work, had some filtration preserving property. So does this?
Yeah.
The W12 is built in a slightly different way.
The
So
one parameter family of metrics has no effect on the filtration, right?
Yeah.
Because the issue is that there's a non-trivial bundle on this, which means that there's a correction factor for what happens to the filtration. I'm gonna guess that the inequality you get here, and by say I'm gonna guess, I mean I know this, it's written down somewhere, I just don't have it on hand right now. I think it looks something like this. Maybe the other way around. Sorry about that. The point is your degree shifts coming from a degree shift formula, and your Chern-Simons shifts coming from the contribution of C1 squared of your non-trivial bundle. But the degree shift wins in the end. So let's see how I can work this out. Is this the right formula? No. I think the right formula is this. If y is the same as y prime, you can iterate this to get something along these lines. Kappa y of d plus 24 is bounded by kappa y of d minus 1. Maybe this is a plus 1/8. Anyway, you end up getting some silly contradiction like this. The constants work out such that if you iterate this and use periodicity, the degree constant has beaten the Chern-Simons constant. You end up getting an inequality, an impossible inequality. Is that what you were looking for, Danny?
Yeah. No, I just was curious as to how
the numbers here are almost certainly wrong. I did not check those.
Yeah, no, we won't hold you to it.
Great.